Hello everyone and welcome to FridaSec. We all know that Frida is the king of dynamic instrumentation, but the industry has caught up. Today, modern RASP solutions like the one we are going to use for this demo called GarudaDefender are specifically designed to detect and kill Frida on site. As you can see, it is currently detecting root, and as soon as we attach Frida to it, it detects that as well and closes the application, right? So if we want to stay ahead, we need to change our toolkit. Today, we are going to dive deep into a new framework called Renef, which is a lightweight, stealthy dynamic instrumentation framework that utilizes Lua scripting APIs to slip past detections that standard tools can't touch. So let me introduce you to this new framework, which is fully open source and its comprehensive information is available over here. Let's have a quick look at the introduction section first. Right now, Renef supports only Android ARM64 applications, and it's designed with real-world security work in mind. It already covers many of the common scenarios you run into during actual pen testing and reverse engineering engagements. These are some of the key features of this framework which it currently supports. First one is ARM64 native function hooking. So one of the coolest things about this feature is that it gives you two different ways to hook native functions. The first method is PLT or GOT pointer redirection, and the second is inline trampoline hooking. Then the second feature is about Lua scripting. So this is their scripting engine which allows us to write hooks using high level APIs in Lua programming language. It is very much similar to Frida Java scripting, but it's much more lightweight and leaves less footprint on the device. Then the third feature is process injection. This is actually one of the key differentiators compared to Frida. With Frida, the framework typically relies on ptrace to spawn or attach to a target app. And in the process, it maps several Frida related artifacts into the memory, which can be sometimes detected by security checks or various RASP solutions. Renef, on the other hand, takes a different approach. It uses a process injection technique that places its component directly into the running process of the target application without relying on ptrace. Because of this, it can operate in a much more stealthy way. Then the next one is memory operations. So similar to what Frida has related to memory like memory.scan API or memory.patch code API, right? Renef also has these APIs to perform memory related operations like scan, read, write, and patch. Then these two features are related to the user experience or user interface, live scripting and interactive terminal UI. So basically with live scripting feature, it allows you to load multiple scripts directly from an interactive shell. So you don't have to restart or reconnect the Renef client every time you want to load a new script. You can just push them on the fly, which makes testing and iteration much faster. Then the last one is about Java hooking. This feature will allow you to attach hooks onto the Java functions. Now let me also show you its abstract architecture so that you can understand how things are interacting with each other under the hood. So basically this Renef framework consists of three main components. First one is the Renef client. This Renef client will be installed on your host machine. Then the next component is Renef server. So this is a ARM64 Android binary which you need to push on your Android device. This is very much similar to Frida server. Then the third component is payload. This is the crucial component. It's a shared library which gets injected into the target process. Let's understand this better with the help of this communication flow diagram. Starting on the top left, we have the host machine. This is your PC, your hacking station. Running here is the Renef client. This is where you reverse engineer, type your commands, load your scripts, and control the entire instrumentation process. Next, look at the arrow connecting the host machine to the Android device. It says TCP 1907 ADB forwarded. Now you might be wondering, why do we need a TCP port open between the CLI and the server? The answer is physical separation. Your PC and the Android phone are two completely different machines. To get them to talk, Renef leverages Android debug bridge. By running a command like ADB forward, it binds a local TCP port 1907 in this case on your PC to a TCP port on the Android device. It allows the CLI to send commands over a standard network socket, but once those commands hit the phone, the networking game changes. Over on to the right side, inside the Android device, the Renef server is listening on that forwarded TCP 1907 port. Okay, it receives the commands sent via Renef client, but the server itself isn't what hooks the app. The server is the manager. Its job is to inject the payload into your target app. Now, look right below the server. This is where the fileless injection happens using memfd plus shellcode. Instead of writing a suspicious .so file to the Android file system where anti-cheat engines can easily detect it, Renef uses memfd, which stands for Memory File Descriptor, to create an anonymous file directly into the RAM. It then uses some shellcode injection techniques to force the target app to load that RAM-only file. As a result, the payload drops straight into the app's memory without ever touching the disk. In this diagram, there is a missing link, which is the secret sauce that separates this tool from other tools like Frida. Like I mentioned previously as well, it uses Unix domain sockets UDS. So once the payload libagent.so is injected into the target process, how does it talk back to Renef server? It does not use TCP. Why? Because opening more TCP ports on the Android network stack is noisy, slower, and can trigger security alerts. Instead, Renef uses Unix domain socket for inter-process communication. So in short, the communication between the Renef server and the injected payload happens with the help of UDS protocol. When we use Frida, this communication happens using TCP port. So if you have already dealt with some of the RASP protections, with some of the RASP solution, you must have discovered that when you run Frida server, the target application detects it based on the open TCP port. So this is not going to be the case over here. All right, so now I hope the basics are clear. Let's get started with the installation and setup part now. For that, we can go to the installation and build section. Here it shows you all the requirements needed to install this tool, followed by the quick start commands. The first command is git clone. I am going to do the same step by step so you can follow along. Let me just copy this command and move to a new terminal and paste it over here. Enter. Once it's cloned, you will get this directory with the name Renef. Next, as per the documentation, we have to go inside this directory. Here we have all the required files to build this tool. Now the next command is to set up dependencies using make setup. Enter. But before running this command, make sure that you have the Android NDK downloaded and its path is configured. Then the next step is to build everything using make command. And it will start building this tool. And at the end, the built binaries will be located under this build directory. So we have this build directory over here. Let's navigate inside it, list everything out. Inside this, we have to go into the Android directory. And over here, we have our libagent.so, which is the payload and the Renef server, right? Now, what you can do is you can either push these files manually using ADB commands or use their pre-built deploy command. So if you have a look at their documentation again, we have make deploy command, which will automatically push these files on your Android device and set the desired permissions. So let's do that. Make sure your device is connected. So my device is connected via ADB. And now, firstly, I need to go back to the main directory. And from here, I can simply run make deploy, enter. And as you can see, started deploying to Android. It automatically pushed this Renef server to slash data local temp directory. Then it changed the permission of the Renef server to executable. Then it pushed the payload to a hidden location. Then it set the permission to 777, which is executable globally. Also, it has set SE Linux context. So all this was automatically done via this simple deploy command. All right, so the setup and the installation is done now. We can move on to the next section. Let me clear it out and go inside the build directory. Over here, we have this Renef binary available. So this is the Renef client. If you remember at the beginning, when I was explaining the features, I told you that it has an interactive shell, right? So we can launch that interactive shell simply by running this Renef client on our host machine like this. enter. And as you can see, it has automatically identified the connected device. It has automatically forwarded the TCP port via ADB on 1907. And now we are inside the Renef interactive shell. With the help of help command, we can see all the available commands, and we can start sending these commands and run our Lua scripts to perform dynamic instrumentation right from here. Firstly, we, just like with any other instrumentation, we either need to spawn the target application or attach to an already running applications process, right? For this demonstration purpose, I am going to use GarudaDefender application, which you can find over here. It's an Android RASP project. They have made their sample application available to public on their official GitHub repository. The reason why I chose this app is because it has some very interesting detection techniques, as you can see over here. It has anti-hooking, it can detect inline hook, PLT hooks, Frida hooks, Java hooks. So it mostly cover all kind of hooking. Then it has dynamic tamper detection. So it is able to detect if bytecode is modified or if any native library is modified. Then it has anti-Frida mechanism as well. So it can detect any modified Frida framework. Similarly, it has anti-debugging and breakpoint detection. So it can detect debuggers like GDB, ADB. It has anti-emulation, anti-instrumentation. It has memory protection as well. Then it has root detection, emulator detection, memory patch detection, right? So this is a perfect app to demonstrate this framework, because more or less we are going to use features like hooking. So for that it has anti-hooking. We will see whether it will be able to detect our hooks or not using Renef framework. Then it has dynamic tamper detection. So when we try to hook any Java function or any native library function, its code in the memory at runtime gets modified. So it will be interesting to see whether it is capable of detecting that as well or not. It has memory protection as well. And Renef has the feature to scan, read, or patch memory, right? So we will see that. So more or less, this application will cover all the features which Renef provides, which makes it a good target app for the demonstration. If you want to follow along, feel free to download the Garuda Defender APK file directly from their GitHub repository. I have already installed it on my device, as you can see over here. So it's currently detecting root, although I have already configured tricky store and using a patch, which is a kernel based routing solution, but still this app is able to detect it. This suggests how strong the protection mechanisms are in this app. Now let's observe the app's behavior, how it reacts when we spawn it using Frida first. So let me just quit this terminal for now, clear it out. And Frida server, I have already started it on the device. So in order to spawn the application, all we need to know is its package name. And to spawn the application using Frida, we have Frida-u-f to forcefully spawn the application, followed by the package name, which I have already extracted from the APK, which is com.kickyps.crackme. Let's hit enter and see what happens. As you see, the target application got spawned and immediately it got crashed. We got instruction abort exception, which usually suggests that the application terminated itself, most likely because it detected something suspicious. Now you might be thinking, alright, if spawning causes a crash, why not just attach to an already running app, right? That way we should still be able to instrument it, right? Let's see. I'm going to launch the application normally on my Android device. Okay, now let's first get the PID for this application using ADB shell ps-a, and I'm going to grab it to capture only the Garuda app, which contains crack in its package name, right? So this is the process ID of this currently running Garuda Defender application. Let me just copy it, and using Frida-u-p followed by the process ID, I'm going to attach Frida to this Garuda Defender application. Enter. Okay, a small typo over here. It's just Frida. Enter. And as you can see, it detected something and closed immediately, right? This time it says debugger detected. So what's actually happening here is that the application is running multiple detection checks asynchronously. Whichever check triggers first is the error you see. If we launch it again, we might get a completely different detection message. Clear out the terminal. Let's give it one more try. Extracting the process ID, which is 19688 in this case, and using Frida-u-p, let's attach Frida to this process. Oops, again typo, it's capital U. And there you go. This time it says hook detected. So it's pretty clear the app is actively monitoring for instrumentation attempts, especially anything related to Frida or hooks. And honestly, this is the exact point where most researchers and pen testers end up spending a lot of their time during an engagement, fighting with these protections, right? Trying to bypass them. That's where a framework like Renef can really starts to shine. Let's now observe the behavior using this new Renef framework. So let me again launch the Renef interactive shell. But before we start sending commands and spawn the app, we also need to start Renef server, right? During the deployment step, it already copied Renef server into /data/local/temp directory of our Android device. So let's go to another terminal and go into ADB shell using su. Let's become root and then go to /data local temp directory. Over here we have Renef server located, right? Let's run it using /Renef server. Enter. As you can see, it's using UDS transport, which is stealthy and hard to detect by many RASP solutions as of now. So the server is in listening mode, waiting for the client connection. We can now start interacting with it from our interactive shell. Now let's first try to spawn this GarudaDefender application using spawn command from Renef interactive shell followed by the package name, which is kickyps.crackme. Hit enter. There we go. The application is spawned. As you can see, still says the device is rooted, which is fine. We did not get any of those messages like debugger detected or hook detected, right? And nothing in the terminal as well, no crash logs. There is still a root detection warning, but that's unrelated to our instrumentation framework. That's coming from the app's own root checks, not from what we are using to instrument it. Alright, so now we are successfully inside the apps process. From here, we can start doing what we came for, hooking functions, performing memory operations, and pretty much any dynamic instrumentation task you would typically want to do during analysis. Now, before starting with the dynamic instrumentation, the first step would be to do a basic static analysis on the target application, right? So let me switch to another terminal. And yeah, before moving on to that part, in the Renaf server logs, you can see the things that has happened in the background when we spawned the target application. So when we gave the spawn command, the server received that command in byte form. It decided to spawn the target application with this package name, and then it started the injection process, or the libagent.so file was injected successfully into the. All right, so here I have the Jadx GUI already opened. Now to perform the static analysis, all we have to do is simply load this Garuda Defender APK file, which I have under trainings 2026 Android Renef Framework demo and GarudaDefender.apk. Open, and there we have its resources and the source code. Let's have a quick look at its classes and methods inside it. If I go to Android manifest file, over here we can see that the default activity or the launcher activity for this application is under com.kickyps.crackme with the name main activity. So let's go inside that directory com kickyps crackme. Over here we have this main activity. Let's load it. Here is the decompiled code, but as you can see, most of the methods were not properly decompiled by this Jadx tool, which suggests that the application is heavily obfuscated and it's quite big activity. There are a lot of methods, even the functions which are properly decompiled. You can see that there are a lot of while loops, if conditions, switch cases. So yeah, basically the Java layer of this application is heavily obfuscated. That's what we can conclude. But the goal of this video is not to dive into how we can deobfuscate or bypass every protection. Instead, I will focus on showing you how to hook both the Java functions and native C functions using the Renef framework. And due to its stealthy nature, we should be able to intercept and trace a lot of interesting things. So to demonstrate the Java hooking part first, let's try to figure out something from this main activity. So over here we have a string tag containing some weird long string. Similarly, we have app URL, JSON URL. Then we have a array of strings with the variable name text containing again some weird string, right? Which is being passed to this myString method. So this looks interesting, and by looking at this myString method, it is indeed a native function taking string as input and returning string. So by looking at its signature and the way it is being called in the Java code, this string, we can think of it as an encrypted string, which is being passed to this function, which is going to decrypt it and then store it into the text variable. So this looks like an interesting method, kick yps.myString. Let's try to hook this method. And like I said, Renef Framework makes use of Lua scripting engine instead of JavaScript. So for that, we first need to create a new file with the .lua extension. So for that, let's go to a new terminal where I am demonstrating Renef Framework demo. And over here, we can create a new file. Let's call it java_hook.lua. Enter. Now you must be wondering as a beginner how to know the API names, how to know the signatures and things like that. So to begin with that, in the documentation part of Renef, we have a section with the name Lua API reference. All the APIs are properly categorized into various subsections. So for example, if you are looking for the APIs related to Java hooking, then you can navigate to this hook API section. Over here, firstly, it has provided a code snippet to hook a native function, but currently we are looking for Java hooking. So just below this, we have a code snippet for Java hooking. So here it demonstrates how you can use hook API to hook any Java function. So basically the API name is very simple. It's hook and it takes 4 parameters. First one is class name, second is method name, third is signature, and fourth is callbacks. So if you have a look at this code snippet, it will become more clear. The first argument class is nothing but the class name where your target method on which you want to attach the hook is defined, right? Then the method name, which is the target method name itself. Then the signature. So this signature needs to be in this specific format. This will tell this hook API like what argument the target function takes and what is its return type. Then we have the callbacks. So this callbacks is a function body which has two callbacks. One is on enter and another one is on leave. So this is similar to what Frida interceptor.attach API has, right? Inside on enter, we can pass the arguments in real time, whatever being passed to the target method. And inside on leave, we can intercept the return value returned by the target method, right? So instead of typing out everything, let's just copy this code snippet from the documentation and go back to where we are creating our script and paste it over here. Now the first argument is the class name, right? So in our case, we want to hook this myString method, which is located under com kickyps.kickypspro, right? Let me just copy it. So this needs to be a fully qualified name, paste, and instead of dots we have to put slash. Okay, and then inside this package we have our class which is kickyps. Let me just copy this and put it over here. So this is the fully qualified class name where target method myString is located, right? And this myString is now the target method name. So I am going to replace the second argument, which is the method name, with myStr. Then the third argument is very critical. And if you made any mistake in the semantics of this signature, then the hook will not be able to work as expected. So right now I'm just getting rid of the default value over here and going back to the decompiled code. Now, the easiest way to get the exact form of signature for this myStr method is by looking at its smiley code. So if I switch from code tab to smiley tab, you will see that this is my target method, myStr, and here is the exact signature of this method. So what you can do is simply copy this all the way up to semicolon, go back over here and paste it as your third argument. And then the fourth argument is the callback body where we have on enter and on leave. Now let's just modify this print statement as well. So instead of main activity, we have kick yps, and instead of get secret, our target method name is myStr, right? This is just for troubleshooting or debugging purposes. This is not something really required to print. Then what we want to do is to print the arguments of this function. So in this case, our target method takes only one argument in the form of string, right? What I'm going to do is, firstly, I'm going to get rid of the second print statement. This is not required anymore. And in the first print statement, I am gonna print param1. Then if you want to concatenate something in Lua programming language, you can put simply dot dot followed by the argument. So now you must be thinking that the first argument would be present at the 0th index of this args variable, right? But there's the catch. This is not like Frida. In Frida, that would be the case. By printing the value of args 0, you would have got the first argument of this mystr method, right? But in this framework, if you have a close look at its documentation, under Java hook arguments on enter, the first value of args, which is pointed out by the 0th index, contains the art method pointer, not the actual argument of the target method. Then the first argument contains the this pointer, which is the instance of the method. But important point to note over here is that if your target method is a static method, then the first parameter of that method will be present in this args1 only, as mentioned over here. And if your target method is a normal method, then starting from the second index of this args variable, you will get the argument of your target method. So this is very important to keep in mind. Otherwise, you will get confused and you will think why I'm not getting the right values. So let's go back to our script, and in the print statement, we have our first argument in args1. Why we are not using args2 is because our target method is a static method. So if I go back to the decompiled code or the smiley code, you can see that it's a static method. That's why to intercept or print its first argument, we have to use args1. If your target method is a normal method, a non-static method, then instead of args1, you have to use args2 to print the first argument. Another important thing to note is that this args1 contains the reference pointer where the actual string or the actual data is present in the memory. So in order to print the actual string value, you have to convert it using jni.getStringUtf method. Okay, so this method is already there documented in the same page. If we scroll down a bit, under JNI namespaces, you will see that to create a new string object, you have to use jni.newStringUtf, and to convert the raw object pointer into a string, you have to use jni.getStringUtf. So now when this function will be executed inside on enter, we should be able to see the argument passed to this mystr method. Now coming to on leave, in this default script, it's actually trying to modify the return value of the method. In our case, we don't want to do it. So let's get rid of these statements. Now inside this print statement, what we want to do is we want to simply print the return value of our target method. So instead of %x access modifier, I am going to use %s, because we know that the return type of this target method is of type string, right? So we want to print the return value as string only. Then just like args1 argument, the return value also contains the reference pointer, but in case of return values, there is a shortcut available, so you don't have to explicitly typecast it using jni.getStringUtf. Instead, to get the value, you can directly use dot value. So whatever the value returned by your target method, that will be printed out. So I think that's all for this script. We can save it. And now in Renef Framework demo directory, we have java_hook.lua script present. Now instead of again launching a new Renef client over here to attach our hook by loading this java_hook.lua script, we already have Renef client up and running over here, and we are inside the interactive shell. So we can directly send a load command to attach our script. For that, there is L command to load the script followed by the script name. Currently, we are inside the build directory from where Renef client is running, and our script is located at Renef Framework demo directory. So we have to clearly mention this. So by going back to directory, we will be in Renef Framework demo directory, right? And over there, we have java hook.lua script, right? Enter. And there you go. All the hooks got triggered. Application is still up and running. So in the logs, you can clearly see that as soon as our hook method, which is mystr, got called, our hook got triggered. And inside on enter, we have printed this statement, right? Followed by the parameter 1 value. So here is the parameter 1 value, which is passed to this mystr method. And this is the original return value which we printed inside on leave callback, right? So without triggering any detection in the target application, we have managed to intercept Java method. This would have been impossible to do without spending hours in order to first bypass Frida detections. So to keep things simple and short, let's wrap this video over here. And in the next video, I will explain you more features of this Renef framework, like hooking native C functions, how we can enumerate all the exported methods from a native library, how to perform memory related operations and things like that. So stay tuned for that because we have just scratched the surface. There is a lot more to this Renef framework. Also, before closing this video, a quick disclaimer. Since Renef is still in its early stages, you might run into some edge cases. So if you notice any weird behavior or crashes, feel free to reach out. I am actively contributing to the project and we are continuously working to improve stability and add new features to it. I hope you enjoyed this video and make sure to like, share and subscribe to the channel.